Consider a translating object, which we treat as a particle. So this can have a velocity and an acceleration. And we consider a stationary reference frame, typically the ground, and a translating reference frame, which has some velocity vt. Now if we measure the distance from the origin of our stationary reference frame, we have a vector rp, and measuring the distance from our translating reference frame, we call this vector the radial vector to the particle p relative to the translating reference frame. So we measure two different distances from each of the different frames. And now we'll take a vector from our ground reference frame to our translating reference frame, which we'll call RT. So using the head to tail method of vector addition, we have the radial vector to the particle measured from the ground is equal to the radial vector to the translating reference frame plus the radial vector to the particle p measured from the translating frame. So this translating reference frame may be a car traveling at some velocity. And now if we differentiate this with respect to time, we have the velocity of the particle p measured by an observer that's stationary in the ground reference frame, which is equal to the velocity of the translating reference frame plus the velocity of the particle relative to the translating reference frame. So this is the velocity of the particle observed by the passenger or driver of a car, for example. So this observer is moving with the car. And if we differentiate again, we get the acceleration of the particle is equal to the acceleration of the translating reference frame plus the acceleration of the particle measured from the translating reference frame. So in other words, an observer in a stationary frame will see a different velocity of the particle compared to the observer in a translating reference frame. And the same applies to the accelerations. And if this frame is not accelerating, so it's traveling at a constant velocity, so therefore the acceleration of the translating frame is 0, then the acceleration of the particle that's measured by the observer in a ground or stationary reference frame is equal to the acceleration measured by an observer in a translating reference frame. So this is what we call an inertial reference frame. And the reason for this will be clear when we look at Newton's laws of motion, which hold in inertial reference frames, or non-accelerating reference frames. A car is traveling horizontally at a velocity of 25 meters per second, and a bus is traveling ahead of the car at a velocity of 20 meters per second west. What is the speed of the car observed by a passenger on the bus? So we have the velocity of the car is equal to the velocity of the bus plus the velocity of the car relative to the bus, or as seen from a passenger sitting in the bus. So the velocity of the car and the bus are from the ground reference frame, or observed by a stationary observer. So the stationary observer will see the velocity of the car as 25 meters per second to the right, and the velocity of the bus is 20 meters per second to the left. And the velocity of the car observed from the bus is VC relative to B in the horizontal direction. So therefore the speed of the car, being VC relative to B, is equal to 25 minus negative 20, or 45 meters per second. So the car appears to be moving towards the bus at around twice the speed. And the correct answer is C, because the speed only has a magnitude and not a direction. Two cars have the following initial velocities. What is the rate at which the distance between them is increasing? So if we have the velocity of car A being minus 3 to the left and 2 vertically, it looks something like this. And car B has a velocity of minus 2 to the left and minus 2 downwards. So the velocity of car A is equal to the velocity of car B plus the velocity of car A observed by a passenger sitting in car B, using our relative velocity equation. So therefore the velocity of car A relative to B is equal to VA minus VB. So minus 3 minus minus 2 gives minus 1 in the horizontal direction, and 2 minus negative 2 gives 4 in the vertical direction. So car A appears to be moving at a velocity of 1 meter per second to the left to an observer in car B, which makes sense. And car A appears to be moving vertically at a velocity of 4 meters per second to an observer in car B. But what we're looking for is the rate at which the distance between the cars is increasing, and distance is a scalar. So we take the magnitude of this velocity to get the speed. So therefore, we have the square root of minus 1 squared plus 4 squared, which is equal to root 17 meters per second. So the correct answer is A. Raindrops fall vertically downwards and hit the windscreen of a car that's travelling east at a velocity VC, and the speed of the raindrop observed by a passenger in the car is one of these answers. So if we take the velocity of the raindrop, that's equal to the velocity of the car plus the velocity of the raindrop observed by the passenger in the car, or relative to the car. So therefore, if we have the velocity of the raindrop as follows, then by vector addition, we have the velocity of the raindrop relative to the car as follows. So to a passenger in a car, the raindrop dropping vertically appears to be coming in at an angle to the windscreen. So by geometry, this angle theta is this angle over here. So we can solve this using trigonometry. So we have tan theta is the opposite edge on the adjacent edge, being the magnitudes of both velocities. So therefore the speed of the raindrop is equal to the speed of the car on tan theta, or VC cotangent theta. So the correct answer is B. Raindrops fall vertically and hit the windscreen of a car that's travelling east at some velocity VC. And what is the car accelerating at? So the car has some horizontal acceleration, and the raindrop is falling on the car under the influence of gravity. So it has an acceleration of g. And using the relative acceleration equation, the acceleration of the raindrop is the acceleration of the car plus the acceleration of the raindrop relative to the car, or observed by a passenger in the car. So by vector addition, we see that AC plus the acceleration of the raindrop relative to the car is equal to the acceleration of the raindrop. And this angle here of theta is equal to this angle. But let's solve this problem using the horizontal and vertical components of the acceleration. So in the horizontal direction, the raindrop has no acceleration because it's falling vertically, and we have the acceleration of the car being horizontal minus the magnitude of the acceleration of the raindrop relative to the car sine theta in the horizontal direction. And the vertical acceleration of the raindrop, which is downwards, is equal to the acceleration of the car in the vertical direction, which is 0, minus the magnitude of the acceleration of the raindrop relative to the car, cosine theta, to get the vertical component. So if we take the acceleration of the car to the left-hand side and divide the two expressions, we end up with the acceleration of the car on a gravitational acceleration is equal to sine theta on cosine theta. So therefore the acceleration of the car is g tan theta, and the car was travelling east. So therefore the correct answer is B.